Alright, this is the second video on section 16.7 about the surface integral. And then this video is going to be a short video, and I'm going to introduce just one thing, which is about orientation of the surface. But before getting into that, let's just briefly recall this stuff about parametric surface. Suppose you are given a parametric surface of uv, so each component is a function of u and v. And then we have defined r of u and r of v, and they are obtained in this way, namely r of u is obtained simply by differentiating each component with u, and then r of v is obtained by differentiating each component with v. And then we compute cross product of those. And then, by the way, to compute line integral of scalar field, what you need is to compute the magnitude of this. Okay. Then now, also, of course, if you change u and v, if you switch the roles of u and v, namely if you compute rv cross ru, and then what you get is negative of ru cross rv. Okay. Then now, this is like the sort of opening remark for this section, for this video, and we'll see this a little later. But keeping this in mind, let me start with what we do in this section, in this video. That's about orientation of surface. What is that? Well, in order to motivate the idea, let's recall. Suppose you are given a curve. Oops. A parametric curve of t. Namely, it's a curve like this. And then we have, so to speak, the orientation or direction. So that means even if you have the exact same curve, it has two different directions, namely either going this way or the other way. Right? And also, if you have a closed curve, namely it's like a circle, we actually define the counterclockwise orientation as positive orientation, and then suppose you have the exact same curve. It doesn't look like exact same curve. It doesn't look like it. Maybe okay. Let's assume that this is the same curve. But if the orientation is, what direction of the curve is clockwise, we say it's negative orientation. Negatively oriented curve. Negative orientation. All right. Then now, what we're gonna do in this video is to do the same for surfaces. So for surfaces, what is the orientation of a surface? Well, orientation of a surface is actually a consistent choice of unit normal vectors. What is that? Well, let me just write it down. A surface is a consistent choice of a unit normal vectors on the surface. Namely, suppose you are given a parametric surface of UV, then suppose surface looks like this. And then there are basically two choices. Two such choices, namely consistent choice of normal vectors, namely, suppose you have surfaces, either in this picture upward, so at each point on the surface, we associate a unit normal vector, namely a vector with length 1, perpendicular to the surface. That's normal vector, unit normal vector like this. This can be said to this can be called a upward orientation. So that's one orientation of the surface. And then the other one is the opposite to it, namely downward orientation. Namely, at each point on the surface, you associate unit normal vector perpendicular to the surface, but that's the opposite direction to the other one. So this is downward. And that's it. And I say consistent choice. And what does that mean? Well, that means if you choose normal vectors like this, at this point you choose this way, and at this point you choose downward, upward, downward, upward, and so on. Okay, this would be inconsistent. You can't really continuously choose vectors, normal vectors. So this is not consistent. And of course, there's more rigorous mathematical way of defining what is meant by consistent choice and not non-consistent choice. But for the sake of this course, this is enough. Just know it more like intuitively, like this picture. And then, so that means if you have a closed surface, what is closed surface? Closed surface is like a sphere, so that you have both inside and outside, like sphere. And if you are trapped inside, you cannot get out. That's what the closed means. And for closed surface, like a sphere, there are two different orientations. One is unit normal vectors at each point pointing outside, or so to speak, outward orientation. And the other orientation is inward. So at each point on the surface, you associate a unit normal vector pointing inward orientation. And then we call the outward orientation the positive orientation. So this is a positive orientation. Just like counterclockwise orientation was called positive, we just call outward orientation positive orientation. We call this negative orientation. Okay. All right, and then let me just mention a couple remarks. A surface with an orientation it's called an oriented surface. Then now, but more mathematically, let's go back to now this, what I briefly recalled at the beginning. Suppose you have a parametric surface, and then we know this kind of a cross product, RU and RV. And remember when I first introduced this guy, this one is RU, and this one is RV, and then this spans, those two span tangent plane to the surface. So that means if you take the cross product of those, what you get is a normal vector tangent to the plane. Not tangent, I'm saying normal vector perpendicular to the plane, tangent to the surface. I'm sorry. Okay, so that means, look, given the parametric surface, RUV, this one, this cross product gives at least a direction, one direction or one orientation. And that means if you look at the other cross product, the opposite to it, that is U cross V, gives the opposite orientation. Well, strictly speaking, in order for this to be an orientation, it has to be a normal vector, consistent choice of unit normal vector. And indeed, here, this one is a normal vector, to the surface. And it might not have a magnitude 1. So if you now make it into a unit vector, this guy, this is a unit normal vector. In other words, this vector basically gives the orientation of the surface. And as we will see for surface integrals, this guy, this cross product, is one of the key players. But for now, let me just mention that this vector gives an orientation of the surface. Okay, so for example, let's consider this. Consider x squared plus y squared plus z squared is equal to 1. Parameterized by, so it's a sphere with radius 1 with center of origin. Parameterized by, so since it's a sphere, we use spherical coordinates. So instead of uv, we use phi theta. It doesn't really matter that much. And by using the spherical coordinates with the radius 1, we get sine phi cosine theta I plus sine phi sine theta j plus cosine phi k. Okay, then now the question is, does this give the positive orientation? Meaning outward. Positive means, remember, outward orientation. Well, here's the answer. Well, we already know this cross product is computed as this. Sine squared phi cosine theta I plus sine squared phi sine theta j plus sine phi cosine phi k. But this was done before. Actually, or you may just do it now if you like. I'm not gonna do it. I just straightforward exercise to compute this. And then, well, is this outward or inward? If you just look at it, it's hard to tell. So the way to check which one is which, we just use a one, so to speak, test point. Say, namely, just pick up one point you like on the surface. Let's say in this case, 1, 0, 0. The 1, 0, 0 corresponds to what? Phi is pi half and theta is 0. Namely, let me just write down the picture. Like this. And then 1, 0, 0 is here. And this corresponds to theta is 0. And remember, phi is the angle from the z-axis. So phi is pi half. X. Then, if you plug in pi half 0, to this one, if you plug in pi half 0, and then this is what? Well, sine pi half is 1, and cosine 0 is 1, and 1 and 0, and 1, 0. Okay, so that means this is I plus 0j plus 0k, or if you prefer, you may write that 1, 0, 0. So 1, 0, 0 is the vector pointing outside in this way. Right? That's a direction of 1, 0, 0. So this is the vector 1, 0, 0. Okay, this is pointing outward. So therefore, the upshot is this one gives the outward orientation, namely the positive orientation. Positive. Okay, so that means, so that's the answer. So the answer to this question is, does this give the positive orientation? The answer is yes. Okay. And also, let me just note that if you switch theta and phi, this gives negative. Okay. All right. So let me just summarize. After all, what you have to know for this section, for this video, is this. Given u and v, and then there are two orientations. And then one of them is given by this, and the other one is given by the other one. And one is the opposite to the other. And then depending on the problem, you have to figure out which one is the right one to use for the sake of surface integrals of vector field. And that's what I'm gonna talk about in the next video. But for this video, that's pretty much it.